Hello and welcome. In this video, I'll be talking about my school project, the Tibetan singing bowl, where we did the simulation to the vibration of the bowl in COMSOL Multiphysique, and then we validated the results using experiment. So let's go and start with the simulation process. So in COMSOL, to get the eigenfrequencies of a structure, you will go to the assistant mode, choose 3D, structural mechanics, and you click on solid mechanics, add, and then go to study. And you will choose eigenfrequency, and it's done. And the steps are, you will create geometry, choose the boundary conditions, add the mesh, and start the compilation. And here are the steps. You need to create the geometry, and that could be done simply by a rotation of the cross section. After that, you will convert your geometry to a solid and add the material and boundary condition. For the wall, I chose the boundary condition to be fixed at the bottom. As we will see later, this boundary condition caused some differences between the numerical results and the experimental results. And at the end, you need to choose a mesh. And for the choice of the mesh, it is better to choose a mesh that gets you to the solution with the least amount of calculations. And for that, I will show my study for convergence. So in these two graphs here, you will see how the eigenfrequencies of the ball change according to the size of the mesh. And on the right, you will see the time of calculation. For extremely fine mesh, the calculation takes about 5 minutes. But when you see the graph, it is clear that you don't need to go that far in the mesh, since after normal size of the mesh, the solution doesn't change. And that means that reducing the size of the mesh is no longer necessary. So here we will simply choose the normal size, click on build, and the last step is to start the calculation. And here you can choose how many eigenfrequencies you need. So let's say we want the 10 first eigenfrequencies, and you will click on compute. So here COMSOL reached the solution, and here we have the first 10 eigenfrequencies with the corresponding deformation. The first comment we can make is that for axisymmetric object, eigenfrequencies come in pairs, which is the same form of deformation with a rotation in space. You see here in the values, you will have two seemingly identical values, which are pairs. Here are the first pair, second pair, third pair, and the last pair. And since we asked for only 10 eigenfrequencies, we didn't get the 11th pair, which would be here normally. And now let's see the form of deformation of these pairs. So here we can see the first pair, and this one is the second. Mind you that they are exactly the same with the rotation in space. And here we have a graph that shows this phenomenon. Because of the symmetry of the geometry, at a point you will have, for example, let's say antinodes. This is the first possibility. And in the second possibility, these points will be nodes. And this point here that was a node in the second orientation would be a node. And we could even see that in the third mode in COMSOL. Mind you that this point here is a node and these two are an antinodes. But in the second combination, this point becomes a node and these two became an antinode. So now let's go and try to compare these values to the experiment.